Every aircraft in history, from the Wright Flyer to the SR-71 Blackbird, has been trapped in the same endless battle. Lift wants to pull it to the sky, drag wants to slow it down, thrust wants to push it forward, and gravity wants to ruin everybody's day. Today, we're going to see how these forces work together to turn a giant pile of metal into a flying machine. Airplanes are basically metal tubes with wings attached, battling the laws of physics to fly. We've already covered the principle behind how wings generate lift in the previous video. So if you'd like to check it out, you can click the pop-up right here. If not, you can stay and watch. If you haven't and don't want to, here's a quick summary. This is Bernoulli. He fought with this guy about almost everything, wrote this book, fought with this guy again over the book, and died. Some of what he wrote in the book is now known as Bernoulli's principle, and is used everywhere, including in wings to generate lift. Great, we can get an aircraft off the ground. But now we have another problem. Drag, drag, drag. It's the reason planes aren't shaped like bricks, bullets don't just keep on flying forever, meteors light up when falling down to Earth, and why annoying slipstream overtakes are possible. So if drag is constantly trying to slow us down, where exactly does it come from? Well, the first culprit is skin friction drag, also called the no-slip condition, most prominent in subsonic aircraft, where the air molecules create friction with the surface, or skin, of the airframe. This is why the F-16's intake isn't directly sticking to the rest of the fuselage. This form of drag is drastically reduced with laminar flow, like that trend where you put tape on a balloon filled with water then poke it. This is why modern aircraft like the 787 are designed with laminar flow surfaces, to keep that boundary layer as calm as possible for as long as possible and save fuel. Alright, we've solved the problem of air rubbing against the aircraft. But why don't we just shape airplanes like refrigerators and call it a day? Because form drag comes into play, which is formed when designers don't know how to shape buses in any way other than a brick. It's caused by the blunt shape of the brick-like vehicle separating airflow early, creating a region of low pressure and sucking the vehicle backwards. A slick and streamlined body solves this problem by delaying separation. Then there's induced drag, the debt collector. It's the aerodynamic cost of generating lift. Any wing sheds vortices off of its tips, and those vortices induce a downwash across the span that tilts the lift vector slightly rearward. That rearward component is the reason the aerodynamic force isn't entirely vertical. Induced drag is, logically, more prominent at low speeds and at high angles of attack. This problem is completely unavoidable. But high aspect ratio wings and winglets effectively increase the aerodynamic span without physically extending it, weakening the tip vortices and recovering efficiency. And don't think going fast will solve your problems, even though it does. Because then you're gonna have to deal with wave drag. Even before you go supersonic, the faster moving air on top of the wing already is. And that's a problem because shock waves form on the wing surface, and these shocks become an absolute wall of energy loss. You can combat this with supercritical airfoils, which delay the shock waves, and with area ruling, the Coke bottle fuselage pinch, smoothing out the cross-sectional area distribution to minimize the shocks that do form. And finally, even if every component is perfectly designed, engineers still have to worry about what happens when those components meet. Interference drag is where two surfaces meet with a sharp angle. This can be minimized by adding fairings, as seen on the F-16, and basically any modern jet. Okay, your flying tube is now slowing down. What do? If you said add some engines, you'd be correct. To combat drag, you need to generate thrust. And to generate thrust, you need engines. It can be propeller, jet, or rocket, as long as we get the aircraft moving forward. So how do these engines even work? Propellers are basically rotating wings. Instead of generating lift upwards, they generate it forwards. So that's that for propeller engines. But jet engines are a little more complicated. They add fuel to and ignite this backward moving air to give it more kinetic energy and generate more force. Afterburners is pouring gasoline into a campfire and hoping for the best. And rockets are so determined to beat drag, they brought their own oxygen supply with them. We'll get into more detail about those in another video, but for now, we just have to understand it's there. By the way, you don't need so much thrust. Unless if your goal is to fly really fast, all you need is just enough thrust to cancel out drag. Okay, so now we have our competitors, lift, thrust, drag, and gravity. But what's the fight like? During takeoff, lift and thrust overpower drag and gravity, accelerating the plane while gaining altitude. But this requires a ton of energy. When you're on a flight and hear the pilot say something about cruising, they just mean the forces are equal for the most part, where lift, gravity, thrust, and drag all cancel out. This is why pilots love the autopilot on long flights. Saves a headache of adjustments. And when you want to land, touching the ground at 1,000 kilometers per hour isn't really safe. So we have to let drag and gravity take the better of us and pull us downwards. Controllably. We've covered how these forces team up in battle with each other. Every aircraft is faced with the same battle, but some fight it differently than others. If you're able to create and balance this battle between these forces and fly, congratulations, you've made an aircraft. If not, you can watch this video explaining how lift is created, or just like and subscribe for more videos like these. Have a nice day.